Dear students, this is Dr. Aisha Nazuk here. Welcome back to my channel. It's been more than a year that I've been running this channel, so I'm glad to say that I've got many subscribers and many students both from within and outside Pakistan who are taking benefits from my lecture series. So today we are going to cover another important lecture related to probability. As you can see that the lecture contents are mainly focused on practice questions, because it's rightly said that there is no shortcut in learning the techniques of probability. The more you practice, the more you get the art of solving these questions. So we will be discussing practice questions related to Venn diagram, combinations and permutations, rules of counting, and then practice questions for law of union and multiplication of events, and then practice questions for conditional probability. By the way, if you want to revise these concepts, like what are Venn diagrams, what is meant by combination and permutation, etc., and these basic concepts, so before watching this lecture video, it's highly advisable that you watch the earlier videos in this probability playlist. Okay, so without further ado, let's start practice questions on Venn diagram. As we know that Venn diagram is a diagrammatic display of a diagrammatic display of relationship between two or more events. So generally we represent the entire sample space using this rectangle. For example, here in this diagram, this white rectangle is the sample space, and we use circles to represent events. So here you can see that event A and event B have some area in common, which is shaded here as black. So I'm going to label it as A and B. This inverted U symbol is either read as AND or intersection, which means the common points in these two events. So now you can see that event A and event B have some points in common, so these two events are non-mutually exclusive. And why these are non-mutually exclusive? Simply because they have some points in common. In other words, they can occur together. That is, there are some points which satisfy the condition that event A occur as well as event B occur, which is shaded here as black. Now we have another Venn diagram. Here I am going to discuss the concept of difference between the two sets. For example, generally you should by now you must have got to know that the sample space is either denoted by S, U or omega, right? So let me show the sample space is either represented by S, U or omega. So omega must be here, yeah. So these are the three notations that are generally used for sample space, right? And what is sample space? You must know it is a list of or a set of all possible outcomes, right? Sample space is a set of all possible outcomes of an random experiment. So these are the three notations that are generally used to represent the sample space. So coming back to this discussion, so if U or this sample space, which I have already told you that the sample space is represented by a rectangle and the sets are represented by circles. So you can see once again we have two sets which have some points in common, so these again are non-mutually exclusive events or sets. So if I, for example, if I consider on this part, this part of the diagram which is outside this shaded area. So what is this area? This is the area, or these are the points which are there in set A but not in set B, right? If you focus only on this part, this is the part which is there in set A but not in set B, right? So we call it's a difference between the sets. A minus B is read as points that are there in A but not in B. Similarly, if you focus on this part of the diagram, the red circle, and excluding this shaded area, now this part of the circle, these are the points which are there in event B or set B but not in set A. So we call it B minus A. So this is how we can represent the difference between two events or the sets using a Venn diagram. Then we will be doing some very basic questions to help you recall the concept of union and multiplication. By now you know that this symbol with circle which is being cut with a slanted line, this is a notation for an empty set. So the question says that if we have a set A and we take its union with an empty set, what will be the answer? You know that the symbol U or union means that you are combining the two sets, that is enlisting all the elements together. So if for example we have a set A and let's say these are the entries in set A, whereas the other set is an empty set, so let me write like this, that there is no entry in this set, right? So you can see that B is an empty set. So what if I take the union of these two sets? Once again that will be A itself, right? Because the set B is empty. So even if I combine an empty set with another set, the answer will be set itself. So here the question is saying what is the union of a set A with an empty set. So the answer will be A, right? Okay. Next question. So what is the union of A and A bar? So now what is the meaning of A bar? It is simply complement of A. For example, if I have this event and this is an A bar, this simply means sample space minus the set A, right? Of course for this we should know the sample space. For example, if the sample space is this, I'm sorry for this typing errors. So if sample space is this and let's say A is this event, so what will be A bar? A bar or complement of A will be all those elements which are there in the sample space but not in A, right? That is exact opposite of A. So exact opposite of A will be 2, 3, right? All those elements which are there in the sample space but not in the set A. So now if for example I have A and A bar, so if I take the union of A and A bar, right, I take the union of A and A bar, so what will be the answer? That is, I am combining all the entries in set A with set A complement. Of course I will get the sample space back. You can see if I combine A and A bar, I will get the sample space back. So the answer of the question, what is union of A and A bar? It will be the sample space. So next we have what is the intersection of A and an empty set. Now this inverted U is read as common point. So what are the common points between a set A and an empty set? So in an empty set we don't have anything, right? So let me write this like this. For example, if there is another set B and it is empty, right? And if I take the intersection of A intersection an empty set, which I have written here as B, so what's the common point between this empty set and event A? Of course there is no common point, so intersection will be an empty set, right? because in an empty set we don't have any point, so there is no logic in taking the intersection of an empty set. So the intersection of an empty set and a set is an empty set again. Next we have, what is the difference of A and A complement? So coming back here, for example, if we have A and A complement, the sets are here, and I want to take the difference between A and A complement. So what does that mean? All those elements which are there in A but not in A complement. Of course we know that A and A complement are exact opposite events of each other. So all the elements which are there in A are not in A complement, because this is the definition of these two events, that they are exact opposite of each other. So A minus A bar means list of elements that are in A but not in its complement. So all the elements in A are not in A complement. So what I'll get back the set A. So the difference between A and A complement will be A itself, right? Similarly, the next question is, what is the intersection between an event A and its complement? Now we have just defined that A and A complement are opposite of each other. So of course there is no point in common in these two events or sets. So the answer will be an empty set. Next we have, what is the union of A and sample space? As I have told you that this Greek symbol omega, this is also used to denote sample space. So if I take union of A with the sample space, what I'll get? I'll get back the sample space, because we know that all the events are subset of the sample space. So if I take the union of any set A with the sample space, I'll get the sample space back. So the answer will be sample space or omega. What will be the intersection of A and sample space? So we know that A is a part of the sample space. So what is common in A and the sample space? Of course A itself, right? Okay, so next we have this symbol. This is read as subset. So if A is a subset of B, for example, I have used this diagrammatic representation of different fields. We know that deep learning is a subset of neural nets or neural networks, which is a subset of machine learning, which is a subset of artificial intelligence. So if, for example, if A is a subset of B, for example, machine learning is a subset of artificial intelligence. So what is common between A and B? So in other words, what is common between artificial intelligence and machine learning? Of course, machine learning itself. In other words, if A is a subset of B, then A intersection B will be equal to the thing which is a subset. So here event A is a subset, to answer will be A, right? If A is a subset of B, then A union B. So coming back here, for example, machine learning is a subset of artificial intelligence. So if I take the union of artificial intelligence and machine learning, what I'll get back the bigger set, which is artificial intelligence. So if A is a subset of B, then A union B will be set B. Okay. So now, before I discuss more concepts, more practice questions related to probability, I want to focus on the fact that whenever you see a probability of an event, keep in mind that it always holds true on average or in a large sample. For example, if we have a coin, we expect that the probability of head is 0.5 and probability of tail is 0.5. But if we do some, let's say if I toss the coin 3 times, it is possible that I get all heads. So what you will conclude, that the probability of tail is 0? No, because when I say that the probability of head is 0.5, it generally holds true in large samples. That is, for example, if you flip a coin maybe 100 times, then you will expect that the probability of head will be approximately or very close to 0.5. So as you keep on increasing the sample size, the expected probabilities, they become equal to the actual probabilities or the empirical probabilities. So whatever we are expecting is a classical probability, and whatever we actually get in repeated trials is an empirical probability. So that is why we often say that whenever we interpret probability, there are certain conditions attached to it, that sample size should be large enough so that we can say that it's a fair approximation. You also need to keep in mind that the experiment should be repeated identically. For example, even if I talk about a coin, so if you are tossing a coin once on a plain area and then on the second trial you are tossing it on an uneven surface, so the conditions are changed. So then you cannot expect that the outcomes will be, or the behavior will be same. So experiment should be repeated identically, and the underlying process, that is the condition of the coin, remains same throughout. And sometimes repeated trials are impossible, because when we talk about textbooks example, for example flipping a coin, it's very easy to flip it 50 times. But in general, when we actually apply probability in practical life, for example, if I want to compute the probability that I clear a GRE exam, so is it possible for me to repeatedly take GRE exam and then compute what is the probability of passing? And is it logical enough that the process is invariant, that is the GRE exam difficulty level remains same? So these are some of the challenges when we go into the advanced concepts of probabilities. We dig deeper into these assumptions, and sometimes we compute complicated probabilities by challenging these assumptions. But that is an advanced level concept. For now, what I want to emphasize is, whenever we interpret probability, these are some of the conditions that must hold true so that we can comfortably interpret probabilities. Okay, so as I said that we are going to do different practice questions in this lecture. So let's say this is a question where we'll be constructing the sample space. So we know that some people are in favor of reducing federal taxes to increase consumer spending. That is, there are some economists or some researchers who would say that if you reduce the federal taxes, it's going to increase spending. While there is another school of thought who would say that reducing tax rate is not a good idea. So let's say if we select 2 persons at random and we record their opinions. So what is the sample space? So here we have only 2 persons, so we can easily enlist the entries of the sample space. So if F represent that the first person favored and N represent that not favored. So FF means that the first and second both person favored reducing the federal taxes. Fn means the first favored and the second did not favor. Similarly, the first did not favor and the second favor, and then the last one should be, this is a typo, it should not be F comma N, this should be N comma N. So pardon for this delay. So the last entry is both the person did not favor reducing the federal taxes. So this is a sample space, and you can see that it has 4 possible outcomes. Another example, let's say the events A and B are mutually exclusive. What does that mean? That they cannot occur together, or their intersection probability is 0. So event A and B are mutually exclusive. We suppose that probability of A is 0.3 and probability of B is 0.2. What is the probability that either A occurs or B occurs, right? Now we know that I have already explained in my last lecture that whenever we have the words like either or, that is either condition A meets or condition B meets. So here we have the probability that either event A occurs or B occurs. So I am going to find the probability of their union. So probability of A union B, if I were to write it in its full form, it is equal to probability of A plus probability of B minus the probability of their intersection. But here the two events are mutually exclusive, so the intersection probability will be 0, and we simply add probability of A and probability of B, so the answer is 0.5. So there is 50% likelihood that either event A occurs or B occurs. Now again, the events A and B are mutually exclusive, and the probability of A is 0.3, probability of B is 0.2. What is the probability that neither A nor B will happen? So it's helpful to have a picture in mind. So I've drawn the Venn diagram here. So if this rectangle is a sample space, and if these two circles are event A and B, as we know that we use circles for events. So you can see that I have drawn the circles in a way that there is no point in common because these are mutually exclusive. Now we want to find the probability that neither A occurs nor B occurs. So the shaded blue area in this diagram, you can see that the complete rectangle is the sample space, whereas this shaded blue area meets the condition that neither A occurs nor B occurs. So we want to find the probability of A complement and B complement. How? Because what is this area? This area is the condition that A complement means A does not occur and B complement means B does not occur. So if we have to find probability that none of them occur, what I can do, if I find the probability that one of them occur, that we just found in the last slide. So if I subtract this from 1, what I'll get the probability that neither A occurs nor B occurs, right? Because 1 minus the probability of the opposite, right? This is that neither A occurs nor B occurs. So what is its opposite? At least one of them occurs. So 1 minus probability of A union B. So the answer is again 0.5. Next we have another example. Suppose that an automatic machine fills plastic bag with a mixture of beans, broccoli and other vegetables. So most of the bags contain the correct weight, but because of the variation in the size of the beans and other vegetables, a package might be underweight or overweight or maybe satisfactory. So let's say we use 3. Event A represent that the package is underweight, event B that the package is satisfactory, event C that the package is overweight. And let's say we have this data, so we can easily calculate the probability of being underweight is equal to 100 divided by 4000 because that's the total sample size. Similarly, probability of satisfactory weight is equal to 3600 divided by 4000. Similarly, probability of overweight is equal to 300 divided by 4000. So we want to find the probability that a particular package will be either underweight or overweight, right? So you can see that these two events are mutually exclusive because at a time a package will be either underweight or overweight. It can't be classified both underweight and overweight. So these are mutually exclusive events. So what I'm going to do, I'm simply going to add the probabilities. So if I add the probability of underweight with the probability of overweight, I will simply get the answer, right? Okay, so next we will also be doing some practice questions that are related to independent events and dependent event. So we know that if two events are defined in such a way that the occurrence of one event does not occur, the probability or occurrence of the other event, they are independent, and if the occurrence of one event influences the occurrence of the other event, then they are dependent. So in this context, a highly relevant concept is the idea of conditional probability. Conditional probability simply means when we update the probability based on the fact that some event has already occurred. For example, if there are two events, probability of A and B, and we know that B is dependent upon A, then the rules of multiplication say that we use the simple probability of A, that is the simple probability of the first event, followed by the conditional probability of the second event. So this is read as probability of B given that A, which is conditional probability of event B given that event A has already occurred. So this conditional probability is only used if the events are dependent, right? If B and A are dependent, only then we use the conditional probability, otherwise we simply multiply the actual probabilities. Similarly, if we have three independent events A, B and C, then their intersection is simply equal to multiplication of their individual probabilities. So let's do some relevant questions. For example, we have classification of different employees in a company. Let's say A1 represent the event that the person would remain loyal with the company, and A2 that the person would not remain loyal. Then we have data on the length of service or years of service. So if you read this table, there are 10 such employees who are expected to remain loyal while they have less than 1 year of experience, and so on. You can read all these numbers. So if I see these total, so 120 is the probability, or 120 divided by 200 is the probability that a person would remain loyal. So by the way, before we actually solve different questions, it's very handy that we draw a tree diagram relevant to this question. For example, if you see in terms of loyalty, there are two possible outcomes: would remain loyal and would not remain loyal. So if I draw the tree diagram, start two branches, would remain loyal and would not remain loyal. So what is the probability of remaining loyal? You can see that all sum of all these numbers is 120, and what these numbers represent: 120 employees are expected to remain loyal and 80 are expected to remain not loyal. So 120 divided by 200 is the probability of remaining loyal, and 80 by 200 is the probability of not remaining loyal. So that's how we have filled these branches. Now a person who would remain loyal and would not remain loyal, there are four different classifications, that their experience is either less than 1 year, 1 to 5 years, 6 to 10 years, and so on. For example, if I were to see how many of those who would remain loyal are expected to have less than 1 year of experience, so what I'll say 10 divided by 120. So that is exactly what I have filled here. Less than 1 year, out of those who would remain loyal, 10 by 120. And this is a conditional probability. Why this is a conditional probability? Because I am imposing a condition that the person would remain loyal. After imposing this condition, then I am computing the probability that that person would have an experience of less than 1 year. So this 10 by 120 is a conditional probability. Similarly, 1 to 5 years, you can simply read from the table, it will be 30 by 120, 6 to 10 year, 5 by 120, and so on. So you can easily see that that's how I have filled these numbers. So similarly, when I'm filling the lower portion, then my reference population is 80 individual. You can see 80 are expected to not remain loyal with the company. So I'm going to divide 25 by 80 if I were to compute the probability of less than 1 year. You see, 25 by 80 and so on. I have filled these branches. Okay, now the question says, what is the probability of randomly selecting an executive who is loyal to the company and who has more than 10 years of service? You see, we have used the word and, so both conditions should be met. That is, loyal and experience of more than 10 years. So you see, I have used this highlighted area. So a person who would remain loyal and he would have over 10 years of experience. So I'm simply going to multiply these two probability of remaining loyal multiply by probability that he have over 10 years of experience. So 120 divided by 200 into 75 by 120, and the required probability is 0.375. Okay, so in the same questions, what is the probability of selecting an executive with more than 10 years of experience? Now here you can see that there is no condition imposed on whether he will remain loyal or not. It's just asking for the probability of selecting someone who will have more than 10 years of service. So there are two possibilities here. Out of those who would remain loyal, there is a branch with over 10 years of experience, and who would not remain loyal, we have a branch with over 10 years of service. So I'm going to add the final answer 0.375 plus 0.150, right? This final answer. And by the way, it's very easy that how this 0.150 is coming. Simply 80 divided by 200 into 30 by 80. So I have labeled the branches here as well, so you can easily read the branches. So if I add 0.375 and 0.150, so what is this branch? This branch represents all those employees who have over 10 years of experience. Whether they remain loyal or not, that's not the question here. So this probability will be interpreted as anyone who has over 10 years of experience. Okay, now we have the same question, but now we will be doing it with an angle of conditional probability. So what is the probability of selecting an executive who would not remain with the company given that he or she has more than 10 years of experience? So you see, conditional probabilities are always used when one condition is given. So here it is given that the person will remain with the company for 10 years. So let's say if I use the word capital T to represent in short that the person will remain with the company, and L bar means he would not remain loyal. So we want to find the probability that he would not remain loyal given that he has more than 10 years of experience. So by definition, conditional probability is equal to the intersection divided by probability of t. So by the way, there is a typo here, so I'm going to correct it, so wait for a minute. Okay, so we have to find the probability that a person would not remain loyal given that he has more than 10 years of experience. So it is equal to the intersection of these two events divided by the probability of the event which is in the given condition. So probability that person would not remain loyal and he has more than 10 years of experience, you can see it is equal to would not remain loyal and over 10 years of experience. So you can see this is this branch 0.150. Now divided by the probability that the person has more than 10 years of experience. So now more than 10 years of experience is possible for the case of the condition who would not remain loyal and who would remain loyal and would not remain loyal. So these are two possibilities. So I'm going to add 0.375 and 0.150, right? By the way, more than 10 years of experience we did here just here in this slide as well. So there is no need to re-emphasize on that on the denominator part because I explained that in detail a little bit earlier. So this answer of this whole thing will be the conditional probability of selecting an executive who would not remain with the company given that he or she has more than 10 years of experience. Another question, let's say the probability that a certain type of machine will break down in the first month of an operation is 0.1. If a firm has two such machines which are installed at the same time, right? Find the probability that the end of the first month just one has broken down. So now you can see that if I focus again on this statement, that the two machines are installed at the same time, right? It's not the condition that either machine 1 is working or machine 2 is working. Both are installed at the same time. So we have to find the probability that at the end of the first month just one has broken down. So this is equal to the probability that A is broken, B is not, or the probability that B is broken and A is not. So since the two machines are identical in terms of the probabilities, so probability of A is broken is equal to 0.1, which is given in the question, and of course not broken is the exact opposite, so that will be 1 minus 0.1. So 0.1 into 1 minus 0.1 plus again 0.1 into 1 minus 0.1, because machine A and B are identical in terms of their probability of breaking down. So if I this 0.18, this is the probability that at the end of the first month just one has broken down, right? Next question, in the manufacturing plant of a company, two large production machines are used. Machine A breaks down with the probability of 0.01, whereas a breakdown of machine B occurs with a probability of 0.005. But if you notice that these two machines are not independent, because if machine A breaks down, then the probability of breakdown of machine B is equal to 0.1. You can see that if machine A breaks down, then it influences the probability of breakdown for machine B. So these are dependent events. So what is the probability that the production stops? So when will the production stop? If at least one of the production machines break down, because you can see the question says in the plant of a company two large production machines are used, right? So if one of these breaks down, then the system is not going to work, because both are required to run the system. So what is the probability that the production stops? That would mean that at least one of them breaks down. So probability of A union B means either A breaks down or B breaks down. So it is equal to probability of A plus probability of B minus probability of A and B, that is A breakdowns or B breakdown minus that both breakdown. So probability of A breakdown is equal to 0.01, B breaks down is equal to 0.005. So but when we are going to find the probability of intersection, then we have to be careful. Probability of A intersection B means, in the question it says that the probability of machine B is influenced with the probability of machine A. So I am going to use the simple probability of breakdown for A, but conditional probability of machine B. So it is given that if A fails down, then the probability of breaking down for machine B is 0.1. So I am going to multiply 0.01 with 0.1, and finally then we get the answer, which is the probability that the production will stop. Okay, next we have another question. Let's say a bag contains 4 white balls and 2 black balls. Then there is another bag which contains 3 white balls and 5 black balls. If one ball is drawn at random from each bag, if one ball is drawn from each bag, find the probability that both are white, both are black, or one is white and one is black. So if I focus on both are white, now both are white means from the bag 1 white ball is drawn, and from the bag 2 white ball is drawn. So in the first bag we have a total of 6 ball and 4 are white. So probability of white will be 4 by 6. So here I have written 4 by 6. Multiply by the probability that from the second bag we also draw a white ball. So total we have 3 plus 5, that is 8 ball, and 3 of those are white. So probability of white from the second bag will be 3 by 8. So if I multiply these two probabilities, it means that from both the bags white balls are drawn. Now if I have to find both are black, that's also similar. So I'm going to use probability of black. So 2 by 6 multiply by 5 by 8. So this is the probability that both are black. So now you will see that I'm going to use this part B to solve part C. So what is part C? One is white and one is black. So it is possible that the white one comes out from the bag 1 and the black comes out from the bag 2, or vice versa. So instead of solving all those possibilities, how about that I subtract the probability of both whites from 1, because if 1 minus both whites mean opposite of both white means at least one of them is one is white and one is black. So 1 minus both white means that now the condition is that one ball will be white and one will be black. So if I subtract the probability of both whites, and then the probability the answer is both whites is here, or both are black, because these are the conditions which are exact opposite of one white one black. If both are white or both are black, so if I subtract these probabilities from 1, then the answer is 13 by 24, which is the likelihood that we have one white and one black. Next we have another question. Box 1 contains 3 red and 2 blue marbles. Box 2 contains 2 red and 8 blue marbles. Now a fair coin is tossed. If the coin turns up heads, then a marble is drawn from box 1. If it turns up tails, then a marble is chosen from box 2. Find the probability that a red marble is chosen. So let's define the event. Let R represent the event that a red marble is chosen, while I represent, or you can say 1 and 2 denotes the event that box 1 and box 2 are chosen. So you can see that a red marble can come out from box 1 or from box 2. So if I use the word or, that means there are 2 possibilities. So I'm going to add the 2 possibilities. Possibility number 1 is that first box is chosen, so I'm writing P of I or P of 1. So P of 1 means the probability that the first box is chosen multiplied by the probability that a red marble is drawn given that the first box was chosen. So this is the first possibility. Then the second possibility is that the second box is chosen and then a red marble is drawn from the second box. So you can see that the likelihood of selection of the box is dependent upon tossing a coin. So since the coin is fair, so the probability of either of the 2 boxes is 1 by 2. So that's why I have written probability of first box is 1 by 2 and probability of second box is also equal to 1 by 2. So how many are red in the first? They are 3, and in total we have 5. So 3 by 5 is the probability of a red marble from the first box. Similarly, probability of red from the second one, you can see it is equal to 2 divided by 10. So then we can simply solve these numbers to get the final probability, which is 2 by 5. Okay, so we have another question. Find the probability that a single toss of a die will result in a number less than 4 if condition number 1 is that no other information is given and condition B is that it is given that the toss resulted in an odd number. So in part A this is simple probability, whereas in part B it is conditional probability, because we are given a condition. So if let's say we denote the event B that the event that the outcome is less than 4. So you can see that there are 3 possibilities, 1, 2 and 3. So on a die, the probability of 1 is 1 by 6, of 2 is 1 by 6 and so on. So there is 1 by 2 is the likelihood that we will get a number less than 4, right? 1, 2 and 3 are the numbers that are less than 4. Now in part B we impose a condition that we know that the toss resulted in an odd number. So probability of an odd number, you can see the odd numbers are of course 1, 3 and 5. So we have 3 numbers that are odd and total there are 6. So 3 by 6 is equal to 1 by 2. Now we need to find the probability of a number less than 4 given that the outcome is odd. So it is equal to, by definition, probability of their intersection divided by probability of the event which is given. So intersection means, what does that mean? If I take the intersection of all numbers which are less than 4 and all numbers which are odd. So you can see the odd numbers from here are 1 and 3. So there are 2 such numbers which are odd and they are less than 4. So 2 by 6, or you can say 1 by 3 if you solve it to its lowest possible form. So 2 by 6 or 1 by 3 is the intersection that the number is less than 4 and it is odd, divided by the probability of odd, which we know is equal to 3 by 6 or 1 by 2. So this is what we get, 2 by 3. So you can see that if we add a condition, the added knowledge that the toss results in an odd number, it has raised the probability from 1 by 2 to 2 by 3. So it is readily evident that whenever we impose a condition, then it changes the final probability. Okay, now we have some examples about rules of counting. So how many 4-digit number can be formed with the 10 digits 0, 1, 2 and so on? In part A it says that repetitions are allowed. In part B it says that the repetitions are not allowed. I haven't solved part C, so please ignore that. So if repetitions are allowed and we have to form 4-digit number, but you can see that I can't use 0 as the first digit because then it won't remain 4-digit. So 0 to 9, there are actually these are 10 numbers, but the first digit should not be 0. So we have 9 possibilities for the first digit, but for the second digit I have 10 possibilities because 0 to 9 these are 10 different digits. So I can use any of these for the second slot. Similarly for the third slot I can again use any 10 of these, and then for the fourth slot I can use any 10 of these, because in part A it says that repetitions are allowed. So 9,000 different numbers can be formed. But in part B it says that repetitions are not allowed. So if repetitions are not allowed, even in that scenario first digit can be any of these numbers but not 0. So there are not 9 possibilities for the first slot. For the second slot, if you focus here, for the first slot we have 9 possibilities. For the second slot we have 9 possibilities. Why 9? Because now 0 is possible. So for example, if 0, 1, 2, 3 so on till 9, if let's say 3 was used in the first slot, so we are left with all options other than 3, and 0 is possible on the second slot. So we have 9 options for the second slot. But for the third one we can't use the number which was used on the second slot, so we have 8 options, and similarly for the fourth slot we have 7 options. So 4536 different numbers can be formed. So I am multiplying 9 into 9 into 8 into 7. So you can see that if repetitions are not allowed, there are lesser possible options. For example, if repetitions were allowed, we had 9,000 different ways, but if repetitions are not allowed, then we are left with 4536 different ways to form 4-digit numbers. Okay, another example of rules of counting: 4 different mathematics books, 6 different physics books, and 2 different chemistry books are to be arranged on a shelf. How many different arrangements are possible if the books in each subject must all stand together? So if I focus on part A only, so you can see that we have different types of books: maths books, and they are 4. So physics books, they are 6, and so on. So for example, if I focus only on the mathematics book, here for example in this diagram I have represented these rectangles as books. So we have, for example, the first math book could be any of the 4. So we have 4 options for the first math book, and for the second it could be any of the remaining 3 maths books, and so on. So we have 4 into 3 into 2 into 1, 24 different ways to arrange maths books. Similarly, for the physics books, there are 6. So we will have 6 factorial. For example, here we have 4 into 3 into 2 into 1, which is 4 factorial. So for physics, I am going to have like 6 into 5 into 4 into 3 into 2 into 1. So that is 6 factorial. Similarly, chemistry books are 2, so that's 2 factorial ways. So I'm going to multiply all these possibilities. So 4 factorial into 6 factorial into 2 factorial into 3 factorial. So this number 207360, this represents the total possible ways in which we can arrange these books. In part B, it says that the condition is that only the mathematics books must stand together. The other subject book may be placed in any order. So if the condition is only on mathematics book, so what I'm going to assume that all other books are, you can say, they could be arranged in any ways. So in total we have that the 4 maths books can be considered as one big book, right? So if for example these are one big book, so how many are left? 6 physics and 2 chemistry. So that 6 plus 2, 8, and treating the maths books as one, so these are like sort of 9 different slots. So we can fill the 9 books in 9 factorial ways, because now we don't have any condition on the other subjects. So 9 factorial ways are possible, but we have treated 4 maths books as one big book, but that I mean they are not actually one, they are 4. So if we have to analyze that how those 4 books could be arranged, we just saw that they could be arranged in 4 factorial ways. So 9 factorial multiplied by 4 factorial, this would give me the answer that the maths books are together, whereas the other subject books could be filled up in any possible ways. Okay, another question: how many different salads can be made from lettuce, escarole, endive, watercress, and chicory? So these are you can say 1, 2, 3, 4, 5 different green leafy, you could say, herbs that are used to make salads. So we can make a salad by using one herb out of these. We can use 2 herbs or 3 herbs or 4 herbs or all 5 herbs. So one herb could be used or selected out of these 5 in 5C1 ways. Similarly, 2 herbs 5C2 ways, and so on. I have added all these, and by the way, why am I using combination? Because order doesn't matter. 5C2 simply means that any 2 herbs are selected. It doesn't matter which herb is selected first. So I'm going to add these combinations. 31 different ways are possible to make a salad using these 5 herbs. Okay, we have another question. A machine produces a total of 12,000 bolts a day, which are on the average 3% defective. So 3% of 12,000 is equal to 360. So 360 are expected to be defective, whereas the remaining 11,640 are expected to be perfect, that is, they are not defective. So we have to find the probability that if we select 600 bolts, 12 will be defective. So that means how many are expected to be defective. So there are 360 total defective, but if we select out of these 12,000, that out of the 600, 12 are defective. So the total are 600 that we are selecting. So 12,000 C 600 represent all possible ways in which we can select 600 bolts. Now we have to find the probability that 12 will be defective. So out of 360, that is the 3% which are defective, we will be selecting 12, whereas the remaining 588, that is 600 minus 12. So remaining 588 will be selected out of those which are not defective. So if you can use scientific calculator easily to compute these combinations, and then you will get the final answer. Okay, next we have an interesting question related to lottery tickets. So let's say in a lottery, each ticket has 5 one-digit number 0 to 9 on it. You win if your ticket has the digit in any order, or you win in part B, you only win if the ticket has the digit in the required order. So in part A, order doesn't matter, whereas in part B, order matters. So for part A, I'm going to use the formula for combination. So there are 10 digits, 0 to 9, there are 10 digits, or I am selecting 5 out of these. So 10C5 is equal to, you can ignore this part, you can use the scientific calculator to compute 10C5, and it is 252. So there are 252 different ways in which you can select 5 digits out of these 10. So your chances of winning will be 1 out of these 252. But in part B, if the digit needs to be in the required order, so the order matters, and I'm going to use the formula for permutation. So permutation of 10 from out of 5 out of 10. So you can once again use the scientific calculator to get the answer, and you'll have 30,240 different ways. So the chances of winning are 1 out of 30,240. So of course in scenario B, your chances of winning will be less than as compared to scenario A, because in scenario B, not only you need to have the winning digit, but they also need to be in the required order. Okay, so next we'll do another example. So next we are going to do another example where we will be discussing rules of counting. So how many arrangements of the letter in Mississippi are there? So you can see in this word Mississippi, there are 11 letters if you count these, right? These are 11 letters. So if I have to fill 11 slots, for the first slot I can say that I can pick any of these 11 letters. So 11 possibilities are there for the first slot, and then for the second slot I have 10 possibilities, and so on. So it seems that it is equal to 11 factorial different ways. But if you have a closer look at this word, for example, the second and the third letter, they are both S. So if I switch the second and the third letter, would it change the original word Mississippi? Of course not. So that means that we need to discount for the repetitions in this original word. So you can see that the letter S is repeated 4 times, the letter I is also repeated 4 times, whereas the letter P is repeated twice. So we have to discount for these repetitions. So what we are going to do, we are going to divide the original 11 factorial divided by the factorial of repetitions. So 4 factorial because there are 4 S, 4 factorial again because we have 4 I's, and 2 factorial for the 2 P's. So these are 34,650 different ways in which we can arrange the letter of Mississippi. So again the root word is Mississippi, and the question is how many arrangements of the letters in Mississippi exist such that the 2 P's are separated. So that means that the P should not be adjacent. So for example, if I delete the P's from this word Mississippi, so I am left with this word. So these are in total 9 different slots. So if I have to pick any letter out of these 9, so we have 9 options, and then for the second slot I have 8 options, for the third slot I have 7 options, and so on. So 9 factorial different options are there, but the problem is we have, you can see, 4 repetitions of S and 4 repetitions of I. So I am going to discount 9 factorial by 4 factorial and 4 factorial. So there are 630 different permutations for if we remove the P's from the original word. But of course P is already there. This is just for our convenience, that or for understanding that we imagine that the P's are not there, but they are actually there. So if I have to out of these, for example, one possibility is that this is the combination, but we have to insert P in such a way that they are not adjacent. For example, if I insert P on the first slot, then the second slot should not be P. So you can see that I have inserted any other letter. Then the third slot, it can be P, right? Then the fifth can be P, and so on. So you can see that these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 different slots in which we have to insert the letter P. So we have to 10 combination out of these 2. So 10C2 means 45. So there are 45 ways to insert P's in such a way that they are not adjacent. Okay, so now what we are going to do, we are going to multiply the 2 possibilities. So in part A we removed the P letter, and we got that we have 630 permutations, and then we analyzed all possible ways of inserting the letter P, and you can see that there were 45 different ways. So if I multiply these 2 events, so there are 28,350 different ways in which we can rearrange the letters of the original word in such a way that the letter P are not adjacent. Okay, so now we have another question. A survey of top executives revealed that 35% of them regularly read Time magazine, 20% read Newsweek, and 40% read US News and World Report. So if I represent these probabilities in this diagram, you can see 0.35% is the probability that a person reads Time magazine, 0.4 is the probability that the person reads US News and World Report, and 0.2 is the probability that the person reads Newsweek. Now 10% read both Time and US News and World Report, so that's why this 0.1 is the intersection of both Time and US News and World Report. So these 10% read both these type of newspaper. So part A says what is the probability that a particular top executive reads either Time or US News and World Report regularly. So you can see these two events are non-mutually exclusive because there is some point or some area which is common, because there are some executives which are reading both of these. So I am going to add in the probability of individual, that is 0.35 and 0.4, but I will subtract the probability of their intersection, which is 0.1. So 0.4 plus 0.35 minus 0.1, it is equal to 0.65, which is the probability that the person reads either of these two or both of these magazines or newspapers. So the part B is what is the probability 0.1 called. So this 0.1 is the probability of their intersection. Okay, so are the events mutually exclusive? No, because they can occur together. That is, there are 10% those individual or executive who read both of these magazines. So these are not mutually exclusive, right? Okay, now we have another interesting questions. A tire manufacturer advertises that the median life of our new all-season radial tire is 50,000 miles. So you can see if I represent this straight line, so if 50,000 miles is the cut point, according to this claim, median life means half of the radial tiles or 50% of the radial tiles are expected to have their life less than or equal to 50,000 miles, and remaining half are expected to have life greater than or equal to 50,000 miles. Now you purchased 4 of these tires. What is the probability that all 4 tires will wear out before traveling 50,000 miles? So assuming that the 4 tires are independent, so probability of wear out before 50,000 miles, in the question it is given that this 50,000 is the median, so the probability of wearing out before 50,000 miles is equal to 50% or 1 by 2, because that's the definition of median. Now probability of wearing out for the first tire multiply by probability of wearing out for the second, then for the third, and similarly for the fourth. And these, we are assuming that these 4 tires are independent, so we are simply multiplying the probability of wearing out for each tire. So 0.5 into 0.5 into 0.5 into 0.5, which is equal to 0.0625. So this is the probability that all 4 tires that you have purchased, they will wear out before traveling 50,000 miles. Okay, another question. 3 defective electric toothbrushes were accidentally shipped to a drugstore by Clean Brush Products along with 17 non-defective ones. So in total there are 20, out of which 3 are defective and 17 are non-defective. So part A, what is the probability that the first 2 electric toothbrushes sold will be returned to the drugstore because they are defective? So in total we have 3 defective. So if the first one which is sold, what is the probability that it is defective? So 3 out of 20. So if the first is sold, then we are left with 2 defective and the total are 19. So probability of second being defective is equal to 2 by 19. Similarly, part B says that probability that the first 2 electric toothbrushes will not be defective. So we have 17 non-defective ones. So the first one non-defective 17 by 20, the second one non-defective, now one non-defective is already sold out, so we are left with 16 non-defective and the total is 19. So the probability that the second one is non-defective is equal to 16 by 19. Okay, another example. Each salesperson Styles competition is rated either below average, average, or above average with respect to their sales ability. Each salesperson is also rated with respect to his or her potential for advancement, either fair, good, or excellent. So we have this table, and people who are their sales ability is below average, they can have potential for advancement as fair, good, or excellent. So we have different possibilities listed in this table. So what is this table called? This table is simply called two-way classification or cross tabulation. Part B says what is the probability that a salesperson selected at random will have above average sales ability and excellent potential for advancement. As I said that whenever you have two type of conditions, it is useful that you draw a tree diagram. So you can see that the tree starts from the two conditions. BA means that the person is below average, and AA means that the person is above average. We can also have the third branch, which is that the person is average. So here we have the third branch, below average, average, or above average. So how many are below average? For example, in total if you see 16 plus 12 plus 22, all these are below average. So you can see that the probability of below average is equal to 16 plus 12 plus 22 divided by total. So total of this table is 500. So probability of below average is equal to 0.1. Similarly, probability of on average is equal to 45 plus 60 plus 45 divided by 500. And probability of above average, I am going to add these probabilities: 93, 72 and 135. So that is the probability that the person is above average. Now out of those who are below average, the probability that they have fair likelihood of advancement is equal to 16 by 50. How? You can see that those who are below average, 16 individuals have fair potential for advancement. So 16 divided by 50, and similarly good, for the probability of good advancement is equal to 12 by 50, and so on. So now we have we can easily fill this tree diagram. Now the question is, what is the probability that a salesperson selected at random will have above average sales and excellent potential for advancement? So above average, so this is the branch, and excellent potential, so this excellent branch is this last one. So I am going to multiply 0.6 with 135 divided by 300, and I will get the required probability for part B. So part C says that we have to make the tree diagram, which we have already done. So these were some of the important practice questions related to probability, and I hope that they are going to help you reinforce the concepts that we have covered in this video. Thank you for watching. Hope to see you in our next video.